G'day viewers. In this segment we're going to talk about specific schemes that can be used to detect errors in packets. We talked previously about errors occurring in packets because of noise at the physical layer. In this segment we're going to go over some specific schemes which can be used to find those errors when they do occur, to detect them. And we will look at three schemes in particular: parity, really mostly for motivation, followed by checksums and CRCs, with the latter two are used fairly widely in practice. I'd point out also that detection by itself won't fix errors, but it will allow us to fix errors by combining detection with a mechanism such as retransmission, and we'll look at retransmission later. Well, let's start with our first simple error detection scheme, parity, or the parity bit. Parity works as follows. You take D data bits and then you add one check bit, the parity bit, and that check bit is going to be the sum of all of the other D bits. That sum will have to be done modulo 2 because we've only got one bit left over to put on. And by the way, this is equivalent to XORing all of the bits together. Here's an example. Let's just say I have 1 0 0 1 1 0 0 as a 7 bits of data to send. If I then want to add parity to it, an 8th parity bit, the parity bit for the case of even parity will be the sum of all of the data bits modulo 2. I've got 3 of those modulo 2. I get left back a 1 instead of a 0, so we add a 1. This is the parity bit. Great, that's essentially parity. And you can check the computation at the receiver. You would go through and add them all up again. Except for the parity bit, you could see if it's if they're equal, or you could just add everything together including the parity bit and you should get 0 out by design. How well does this parity code work? Well, if you recall our concepts of error codes, we can sort of begin to think about it. First of all, we can ask, what's the distance of this code? How many bit flips do I need to make? What's the minimum number to turn any one code word into another code word? Well, in this case, if I flip any one bit, the parity sum will be wrong, but if I flip another bit, then I can get to a place where the parity sum would be right, even though the data has changed. So the distance of this code is 2. Given a distance of 2, how many errors are we able to correct? Well, the answer to that is 0. You don't correct anything. If the parity is off, you get to see if there's been one error, but we don't have enough distance here to be able to correct anything. What about detecting errors? How many errors are we guaranteed to detect? If the distance is 2, we're guaranteed to detect up to 1 error. So that's all that parity is good for in terms of any guarantees. Now, for errors, which, so it's not that strong. For errors larger than a single bit, what happens is going to depend on the structure of the computation. For parity, if you think about it, actually it has this nice property that it will catch all odd numbers of errors, where an error is changing a 0 to a 1 or vice versa. The first error will be caught by parity, the second error will cancel out that parity bit, won't be caught, that was why it's distance 2, but the third error will bring us back to the situation where there's a problem with the parity check bit once again. So we've detected all odd numbers of errors, but not all even numbers of errors. Here's a stronger alternative, and one that's used in practice much more widely today. The idea here is, in a checksum, is to sum up data, much as we did with parity, but instead of using a single bit, we're going to sum up the data in terms of n-bit words and use an n-bit checksum, or n check bits. For example, TCP, IP, and UDP, they all use a 16-bit checksum. This checksum is going to provide stronger protection than parity. We'll find out later it's really not that strong, but it is stronger than parity. I'll give you one specific example, and that is the internet checksum. This is the particular kind of checksum that's used in TCP, IP, UDP, and other internet protocols. Here's the definition of the checksum. The checksum field is a 16-bit ones complement of the ones complement sum of all 16-bit words. Oh my goodness, that sounds very confusing. It's not that confusing once you get used to it. Essentially what it's saying here is that you sum up all of the data 16 bits at a time, and then you negate it, so you come up with the negative sum. The catch here is that all of this arithmetic is done with ones complement addition, and it's done that way to give a better distribution of our data over the 16 error bits. Ones complement notation is a way of describing binary numbers such that the ones complement, or flipping all of the bits of a number, gives its negative form. So for instance, if I have 001, the ones complement version, the ones complement or bit flip of that is 110. So this is 1, and this other bit one is -1 in ones complement. Ones comp. The computers we use perform addition where all of the binary numbers, the integers, are represented in 2's complement form. To get 2's complement, you do 1's complement and you add 1. So for instance, this -1, 110, if I add 1, I would get 111. This is actually -1 in 2's complement. The hitch with using 1's complement addition on a 2's complement or regular computer is that when you add up numbers in 1's complement form, if any of the bits overflow into the carry field, you need to take them back and add them to the low order bits. That's probably a lot more than you wanted to know or bargained for hearing about 1's complement addition. It's really not that bad though, so let's have a look. Here's an example we're going to work through. We're going to calculate an internet checksum. The first thing you do when you want to send data is you arrange the data of the packet to be sent in 16-bit words to sum up. That's these 4 values that I've shown here. So the packet, if you like, read 0001, F2, 03, F4, F5, F6, F7. And I've just laid it out in these 16-bit words to sum. Now we're going to add these together. We'll actually put a 0 in the checksum position here, just so we can have the same algorithm on the receive side. And we're going to add all of these things together. What do we get? Uh-oh, this is making me work hard. Okay, let's see, when we add up these numbers, we get 10, we get 16, so that's actually, is that right? Okay, so 16 is, we get a 0 here, and we carry the 1. Here we'll end up with F, and we'll carry the 1. Now we have 11, 12, 13. 13 in hexadecimal is a D. And here we have 3 Fs, which are all added up. F stands for 15 in hexadecimal. What we're going to get is 20, we're going to 2, and what's left over will be a D. Now, so we've got that sum. Of course, this left bit here is overflowed from the 16-bit position. So what we're going to do is take that back and add any carryover back. So we'll just take those high order bits, D, D, F, 0. We'll add the 2. The 2's moved down here. When we do that, we get D, D, F, 2. Okay, now our final step is to negate by complementing this value, and then we'll get the checksum. So we want to negate all of those bits. Okay, let's negate D. If you remember, if I do the binary representation of D, D is actually 8, 19, 11, 12, 0, 1. That should be 13. When I bit flip that, flip, I'll get 0, 0, 1, 0, or 2. So when I negate that, I'll get 2, 2. Bit flipping F is all 1, so when I flip all of that, I'll just get a 0. And when I flip 2, I'll get a D. So 220D will be the internet checksum. And we will then take that value, replace it where we used all zeros, and then send those 5, including the checksum 16-bit words, out into the network. Okay, it's all cleaned up here, and thankfully I ended up with the right answer. Now let's look at the receiving side. What's going to happen? Actually, exactly the same algorithm happens. We just want to make sure that we get 0 out when we've negated everything at the final end. Let's work through it. It should be the same steps. Here, we arrange the message in 16-bit words. The checksum is there, it's the last word. It's non-zero because it was calculated on the other side. Now we add it. So what do we get? Well, before we have our 16 plus D, so that will be D. We carry the 1. 1 FF, that will be, we'll end up with an F. And we're going to carry a 1 here. 10, 11, 12, oh, guess what? It's, what is it there? 13, 14, 15, so we have an F. And we're left here with FF, FF, 2. So when we add that together to D, we'll get 2F. Okay, now of course we've carried over, so we've got to take this high thing and add it back. So we'll just do this sum, FF, F, D plus 2. What do we get? We get F, 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 F. Oh, this is looking good. When we complement that, we get 0, 0, 0, 0. That's correct. The checksum passes. No error was detected in this packet. And it's cleaned up here. You can see I've highlighted it as good. I already knew I got the right answer because it came out as zeros. So that's how checksums work. What we need to ask, though, is whether they're any good. How well does this checksum work at detecting errors? We could begin by asking, what's the distance of this code? Actually, the distance is not so impressive. This is a sum. So if we want to get the same sum, you can imagine just having errors in 2 bits of the data. In one place, we'll add a certain value, like maybe 16 to a 16-bit word. In another place, we'll subtract a certain value, like 16, the corresponding value from a word. Or maybe we'll add the 64-bit position, and so forth. But the point is, we could make 2 corresponding errors and fool this sum. So the distance is only 2. Well, rats. This means that, as before, the number of errors we can correct is 0. This is just error detection, not correction, so we're not trying to correct anything. But the maximum number of errors that we are guaranteed to detect is actually 1. 2 bits can fool this checksum. Well, has this gotten any better? It has gotten better. So if we think about larger errors, what's detected here is going to depend on the structure of the code. We will actually find all burst errors up to 16. So it's a 16-bit checksum. A burst error is just a sequence of errors in a row, or a window of errors where in that window errors occur. Maybe some bits in the middle are not flipped, but over that window, a small window in space, the error occurs. It's a burst error. So it's an advantage here that if those errors occur in bursts of 16 or less, and there's just one in the packet, we're going to detect it. Because if you think about it, those 16 bits can only be affecting one 16-bit word or 2 adjacent ones in different places, so they can't cancel out. If there are much larger errors, in fact, if we just make up random data, then we will detect random data to random with probability 1 in 2 to the 16. If we just make up data, random data, then since there are 16 bits, there are 2 to the 16 different possible checksum values. So there's only a 1 in a 2 to the 16 chance that the checksum will actually match the data. So this is much stronger than parity. So we have got quite a lot by going from checksums to parity. It's really much stronger. But it's not as strong as we would like things to be in practice. For the same number of bits, we can do even better with codes which are called CRCs, or cyclic redundancy codes. The way a cyclic redundancy code works is you take n bits of data and then you generate k check bits so that when you add them together, the n plus k bits are evenly divisible by what's called the generator, C. I can show you an example here with numbers. So let's just say we're working with decimal digits. The number I want to send is 302, and I'm going to send a 1-digit check. So I'm going to send a message 302 something. We just want to work out what that something is. We want to choose a something so that the whole number, including the end, is evenly divisible by our generator here, which is just going to be the number 3. Well, one thing I can do is I can just start with 302. Let's just add a 0 at the end. And let's just look for the remainder when you divide it by 3. That's equal to what? Well, the 3,000 falls away, 320, that goes 18, so we're left with 2. The remainder is 2. And you can see, since 3 minus 2 is 1, I'm just 1 short of being evenly divisible. So all I need to do is put a 1 here, 3021, and send that. That is evenly divisible by 3. And so I've computed that my check digit there should be a 1. The catch for CRCs is that we need to do all of this based on the mathematics of finite fields. The binary sequences here represent polynomials. So in fact, this binary sequence here represents this polynomial. You can see there's a 0 there for x to the 0 or 1. There's 1x to the 1, no x to the 2's, 1x to the 3, 1x to the 4, no x to the 5's, no x to the 6th, and 1x to the 7. Boy, this could be complicated. What this really means, if we're going to do a complication ourselves, which is a little horrible and grungy, but we'll try and work through it just so you can really get to the bottom of it, is that if we're going to do these CRCs ourselves, we need to work with binary values, and our arithmetic will be done modulo 2. So the send procedure for a CRC is as follows. You take the data bits, and really we're mimicking here what we did with our decimal digit example. You take the data bits, you extend them with k zeros, then you do a division by this generator value. Once you do that, you look at the remainder to see what it is. Keep that, ignore the quotient from the division. And using this remainder, you adjust the check digits by the remainder so that they will be evenly divisible. The receive procedure is to simply divide the whole thing, including the CRC bits at the end, the check bits at the end, and once you've divided it, check that the remainder is 0. If that's the case, there'll be no errors in the packet. Okay, let's try and work through this. Here's an example. We have a sequence of data bits here. You can see I've written them over here. And we're going to divide by our generator, which is 1011. That's the divisor here. The first step, and I have 4 check bits. The first step is to add 4 zeros to the end, since I have 4 check bits. Now, I'm going to do a long division. Wow, this might take a little while. Let's go with our divisor and write it out. So we're going to take away 1, 0, 1, 1. Oh, sorry, good grief. No, it's a 1, 0, 0, 1, 1. When we take that away, what do we get? 1 minus 1, that's a 0, that's gone. 1 minus 0 is 1, 0, 0, 0. 1 minus 1 is 0, 0 minus 1. Sounds like minus 1, which is actually 1 in modulo 2 addition. Okay, now I could write up the top just that the quotient goes here. For instance, I got a 1 here when I divided, but we're not going to keep this anyhow, so I'm going to ignore it. I'm going to keep going on now, taking things away. So now we're down here and we're going to take values away. I'll move down what we've got here. There's a 1. So again, I want to take away 1, 0, 0, 1, 1. Boy, we're in luck. That's the same thing here. So this is all going to go to zeros, all zeros. And now what we're left with is down here. I'm going to copy down these digits. Now I'll continue subtracting 1, 0, 0, 1, 1 from this, and I'll get 0, 1, 1, 0, 1, and I've got another 3, 0, 0, zeros here. Do it again, 1, 0, 0, 1, 1. When I subtract that, I get 1, 0, 0, 1, 0, 0. One more subtraction, 1, 0, 0, 1, 1. Cancel, 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 cancel. I'm left with here 1, 0. And that's the final remainder. What I would like to do then is take that remainder and use it to modify the bits that are transmitted. I would like to send 0 minus that. I would like to add 0 minus that value, so that it'll be evenly divisible. What will end up happening is that we'll basically, because this is all modulo 2, end up putting this value 0010 from the bottom, 0, so these were zeros, up here. And then the checksum bits that we'll send out, sorry, the CRC bits that we will send out will be 0010. That's a little messy. Let me clean that up. And you can see, yeah, here it is. And at the bottom, there is the transmitted frame. You can see it's the data bits, and we computed our CRC to be 0010. Great. Here, there's also a little more information like the quotient, which gets thrown away. And I've shown some other steps here, which were omitted in the middle, just so you can work through that and check it all if you would like. At the receiver, you do the division and you should get 0. We'll skip that in the interest of time. As with checksums, let's think about CRCs for the moment and just ask what kind of protection we get from them. The kind of protection is going to depend on exactly what generator we used. Now, unlike the other schemes, we're not really going to be able to work this out for ourselves. CRCs are based on these mathematics of finite fields. People have calculated over the years good properties of different generators, and in fact, there is a standard CRC which you'll see almost everywhere, even though better ones exist these days. There's a standard CRC. It's defined to be this number. That's actually a polynomial if you write it out. But this CRC is used on Ethernet, Wi-Fi, all sorts of places. This CRC, I'm just going to tell you the properties since we can't really work them out from first principles ourselves. The Hamming distance of this CRC is 4. This means it will detect all errors up to and including triple bit errors. So any 3 errors, 1, 2 or 3 errors, you're covered. 4 errors, there must be some way to get around it. It will also detect, like parity, any odd number of errors. In addition, it will detect all bursts up to k bits in error, where k here, for a 32-bit CRC, that would be 32 bits. And it's also stronger than checksums in that it's not vulnerable to systematic errors. Checksums, because it's simply a sum, if you were to do something like insert a lot of zeros inside a packet, it wouldn't alter the sum, you wouldn't pick it up. With a CRC, if you move data around or add zeros or splice things together, it will pick it up. And finally, to wrap up, let's talk about error detection in practice. CRCs, the strongest form we saw, are very widely used on all sorts of different link layers. They're used in Ethernet and 802.11, as I mentioned. They're also used over your DSL link, cable links, and so forth. They're an industry standard. Checksums you'll also find are fairly widely used in the Internet by all of the Internet protocols, TCP, IP, UDP, and so forth. Compared with CRCs, though, while they're simpler to compute, they're weaker. And I would hazard to guess that if the Internet were being designed today, stronger forms of checksumming would be used. Finally, there's parity, which says there's a good motivating example for us to work through, but it's little used in practice because we can usually afford more sophisticated schemes for error detection.